Mathematics in zeros and ones. This little talk is just a bit of a philosophical thinking about our research. And this is definitely not about how computers are used in calculating some values of a well-known or well-understood functions, but more like how we can use computers in extending and understanding mathematical knowledge. So, the first question is, how quickly can we reach the limits of our mathematical knowledge? And well, the answer will be then very quickly. So let's do some very simple example. Here is a transformation drawn as a diagram. It's a function from a set to itself, and the function is denoted by these arrows, and the set, the elements of the set are denoted by these dots, and this is just saying that, for example, that the fourth element goes to the fifth element under this transformation, under this function. So this object is very simple. Basically, it's finite, and we can basically answer any question about it. But the situation changes when we start combining these transformations. Well, the actual operation of combining them is not that complicated. We just take them and follow these arrows along the connected lines, and of course we need some simplification, but we get another transformation. And we call collections of these transformations that are closed under this function composition and transformation semigroups. And here is one little example. The transformation semigroup basically implementing a 1-bit memory, and it consists of 3 transformations, all defined on a 2-element set, and here are the corresponding diagrams. Well, you can write 0 and you can write 1, and if you use the point itself, sort of, you can have a read operation by just the identity transformation. So these transformation semigroups, these collections of transformations, are sort of computational devices. And now we can ask questions that, well, how many of these for a given number of states, or in other words, what is computable with n states? And we do not know. So here we have an open problem, and it's possible that many people tried and didn't get too far with this problem, or simply just researchers thought that, well, this is a very difficult problem, so it's just better not to try it. So what can we do? Well, we can take a small flat piece of stone or a piece of metal, but that's exactly the point, and draw some intricate crisscross patterns on its surface, sort of nanowires in many layers, and then let just the electrons flow in this pipework. And this is how it looks like. So this is a modern processors with 15 core, and with all these nanowires in it. And here is another one. But okay, there is one point with all this computational research that it's sort of frustrating, that actually we don't see what's going on, because these are happening, the computation happens in such a small scale, and even if you could see it, you could see the electrons flowing, then, well, then exactly that would be the point where you don't see anything. But okay, this is not just our frustration. It's like, as you can see, companies come up with some metaphors. They call these processors bulldozers, pile drivers, steamrollers, and they actually look like this. So processor marketed like power machines. Okay, well, so after using this, and about 2 weeks later and 70 kilowatt hours later, we just know the answers. And there are slightly more than 132 million transformation semigroups on 4 points. And of course, we are not just interested in the number, but we are interested in their properties, and well, actually all of them. So we classify them according to the obvious semigroup properties of interest, and stored in a 9 gigabyte file. So actually now we know a bit more. So let's just think about it, what happened here. Another metaphor. How much did we know about microorganisms before the microscope? Well, ancient Greek philosophers, they thought about it, but that's just on the basis that given enough free time, people will think of everything and anything. So it was just the mere idea. How much did we know about galaxies before the telescope? Well, again, not much. The Milky Way gave itself away because you can see it on the night sky, but there were only speculations about the nature of that phenomenon. And we can ask, how much did we know about the size distribution of all 4-state transformation semigroups? And we knew actually nothing. During the computations, when we had some partial results, our educated guesses were often wrong by 2 orders of magnitude. So our mathematical intuition was really useless for this problem. We couldn't predict this size distribution of these semigroups. So the conclusion is that computers enable us to see more mathematical objects and to observe them closer and more clearly. So with computers we can extend our mathematical knowledge. Obvious next question, what is mathematical knowledge? Well, mathematical knowledge exists in the minds of mathematicians and is written down in textbooks and journal papers. And it also has some structure. It's formed as theorems and proofs. Theorems are statements about mathematical objects that are known to be true. And the proofs are the processes to establish the veracity of these theorems. But they can also be thought of as ways of understanding and communicating the theorem. So knowing the mathematical structure enables you to prove theorems, and by the same token, by following the proofs, you can get to know that particular mathematical object. And while the usual counter-argument is that while computing is just a mindless mechanism that has nothing to do with being clever and actually sort of producing new mathematics. And well, I'm not going to refute that counter-argument here. I'm just sort of talking about our impression of what's going on when we do these computational experiments. So usually what happens when you study a mathematical object, you start with a brute force algorithm, which is really mindless. It just enumerates all possibilities and just looks for the ones that are interested. And that's usually very inefficient. And of course, in all these computational experiments, we fight with time. So we want to do things faster in order to be able to do more. So there are iterated steps when we improve the algorithm. So we use the brute force and we check the results, and we see more, we know more about the object, so we can make the actual algorithm more efficient. So if you think about this process, the algorithm is just converging to the mathematical structure itself. So it forms as a complementary shape, like molding. And this is much like as the genome is becoming more and more precise description of the environment in which the organism has the adaptive advantage. So to put it in another way, writing computer code is a way of understanding mathematics, and we apply this strategy across many projects, and we force our students to write code in problem solving. So one can say that the source code of nature is written in a mathematical programming language. Okay, it's high time to ask this question: what is a computer anyway? Well, a computer is something that stores and transforms information. And if you accept this definition, then this is a computer, a piece of paper and a pen that forms a computing device. Well, you can store information just by writing on it, and you can retrieve information by reading. And of course it does transformation, it does the identity transformation. So in that sense it's a limited computer, but nonetheless it is a computer. So then you can meet the legendary computing geeks of the past, and one reason they did so many great stuff, because they just calculated things, explored mathematical objects all the time. So it's all nice, so we can use computers, and it's not just a mindless mechanism, but it's really getting close to the mathematical object, so it's all happy. But it's not quite, there is a dark side here. And the main question is that, can we trust computers? Well, after 2 weeks the computer outputs a number, and just do you believe it? Of course, we have software and hardware bugs, we face extreme man-made complexity, and probably we can say that even you just take a laptop, no one fully comprehends all the workings of that device on every level. And we all know that we encounter surprises in the forms of software and possibly hardware bugs. So what can we do against this? Well, we can repeat the calculations on using different software and different hardware, and of course having the source code available, and actually looking at the source code and document it is another defense against bugs. And of course we have all the physical world against us. Well, the key thing is that it's a sort of a miracle. You have this little thing as the computer chip, the processor, and it's a fully deterministic physical system, and you just set it up, and hours later you know the answer for some mathematical question. And of course, that's the miracle part, but again, since it's a physical system, there is a dark side here. So it's actually a vulnerable physical system. We have cosmic rays, sunspot, and it could happen that in the memory just one bit is flipped, and that of course would destroy the whole mathematical calculation. So one defense is that using memory modules that has 9 chips on them instead of just 8, and the 9th chip is for the error code correction, the error correcting code. And of course we produce huge amount of data, and it turns out that actually there is sort of a crisis in storage. And of course we have this high-speed technological progress, and it hides the fact that while we can store more and more data, but the longevity and reliability is not really good. You can compare hard drives to clay tablets, and clay tablets do have some advantages. But again, using some clever technologies based on very clever mathematics, we can have self-healing file systems. And probably the biggest question is that whether we are reaching the theoretical limits of computations. And of course, well known the question P versus NP. So are the difficult problems really inherently difficult, or we just haven't found the clever trick yet? But on the other hand, it feels that actually it is possible that the difficult problems we face now are really the ultimate difficult problems. Like in the medieval ages, if you could do, say, multiplication and division of numbers, you were so cool that you were employed by the king himself to do probably tax calculation. But now that problem is not considered to be difficult, it's a routine problem. So, well, again, the question is that is it possible that we just haven't found the clever trick yet? So, conclusions. Well, computing is a formidable tool in pursuing mathematical research. And personally, I can say that while we are chasing the ultimate knowledge by using tools from our childhood science fiction dreams. So, well, it's pretty enjoyable and actually useful. But in a sense, computing might be reaching its limits. And while currently Moore's law seems to be broken, and we seem to have some genuinely difficult problems. And that's why, well, in sort of computational mathematics, we shouldn't forget about that actually computation doesn't scale well in many important cases, but mathematics does scale, because that's exactly what we do in mathematics. We proceed from the case n to the case n plus 1, and regardless of the magnitude of n. So yeah, computing is good, and with the new generations of mathematicians, it will gain more and more importance in mathematical research, but that's just one part of the story. Well, yeah, that's it for this little talk.